and talk a little bit about vector operation, so one way of multiplying vectors together, and this way gives you a scalar. So there are two vectors that go in, and the output is a scalar. So this is called the scalar product or the dot product. So I have two vectors. So I have a vector A, and I have a vector B, and I'm going to put them tail to tail to do their dot product. And what the dot product is trying to tell you is how much of one vector points along the direction of the other vector. So the dot product answers the question, how much of vector A points along the direction of vector B. And so the dot product A dot B, so using the dot is one of the possible multiplication signs. And here in multiplication, if these were numbers, then A could be like A dot B or A cross B, or you could just put the two numbers next to each other. Vectors, it's very specific what you mean. Each one of those different multiplications symbols mean something different, and here we mean the dot product. So what that means is we take the length of vector A, its magnitude, times the magnitude of vector B. So those are both strictly positive. The smallest either magnitude of A or magnitude of B could be a 0. So the sign of the dot product is coming entirely from this cosine theta factor, because neither magnitude of A could be negative nor the magnitude of B. You just write this out in the shorthand. So AB cosine theta. If you're given a vector A and a vector B in component form, you don't have to go backwards to figure out their length and the angle in between them. The other way of expressing the dot product is as follows. So if you're given the components, let's say I have a vector A, some component along the x direction, some component along the y direction, plus some component along the z direction. And similarly for B. In general, it'd be quite a bit of work to go backwards and find, well, what's the magnitude of A to fill in there? What's the magnitude of B to fill in there? And especially to figure out what's the directional angle in between the direction A points and the direction B points. That could be quite a bit of work. And you don't need to do that. Matter of fact, this is how you would turn around and find that directional angle if you ever needed it. A dot B I could also compute by taking the x components multiplied together plus the y components multiplied together plus the z components multiplied together. All right, so try a couple examples of using this to compute work. So let's say I have a force vector and I have a displacement vector. So I have some object that actually goes through the displacement delta r, but simultaneously there's a force acting on it, and we are given that angle is 120 degrees, and magnitude of the force is 5 newtons, our displacement is 1.2 meters, sorry, in magnitude, and then the work done by my force F for that displacement is going to be the magnitude of the force, so 5 newtons, magnitude of displacement, so 1.2 meters, and then cosine of 120 degrees. And that's going to work out to minus 3 Newton meter, and a Newton times a meter is our unit of energy, so that's minus 3 joules. And it's perfectly fine to have work done be negative. That means an object is going to slow down. It's perfectly fine to have a dot product that's negative. That means that at least part of A points in the opposite direction of B. All right, and then in terms of components, let's say I have a force vector with 3 spatial components. So it's 3 newtons along the x direction plus 4 newtons along the y direction plus 5 newtons along the z direction. And I have a displacement that is 1 meter along x minus 2 meters along y and 1 meter along z. Then the dot product of the force with the displacement F dot delta R, I just go through, multiply the components and then add them in. So for the x components, I have 3 newtons times 1 meter. It's going to give me 3 joules. For the y component, 4 newtons minus 2 meters is going to be minus 8 joules. And then along the z direction, 5 newtons, 1 meter is going to give me 5 joules. And I add that all up. 3 minus 8 plus 5 gives me 0 joules. So for that force and that displacement, there's no net work done. And then a quick little bit about the dot product and unit vectors. They behave, hopefully, the way you would expect. That since they have unit length, the x hat dot x hat is 1, y hat dot y hat is 1, z hat dot z hat is also 1. So x points along the x direction and so forth. X dot y is equal to y dot x is 0. No part of x points along y. Somewhere no part of y points along x. X hat dot z hat is equal to z hat dot x hat is equal to 0. Because x and z are perpendicular. And then lastly, y hat dot z hat is z hat dot y hat equals 0. And in general, the dot product is symmetric. So A dot B is equal to B dot A as a general statement.